Okay. Let me share my screen. Okay. I guess you can see my screen, right? Here. Okay. Okay. So this is week 10. Okay, and we are currently focusing on learning these theoretical concepts for reinforcement learning. Okay. So in week 9, we covered clustering algorithms, how to like implement clustering in Python, and also touch, let's say, CLOUD score based. Let's say I don't know how many clusters will be there, so uh, basically use a metric to get around which how number, like how many number of clusters would be optimal for my data. And then we kind of touch little bit on reinforcement learning. Okay, so today we will be covering covering it in a bit more detail. Okay, and also I will show you some good libraries that you can play with. Okay, so let's start. So that agenda is this. So this Markov descent process, we can also think of it as a game. Okay, so what is kind of, so how games are formulated in reinforcement, that that we will understand, and some concepts, some theoretical concepts like return value, then policy. Okay, these things we will understand first, and then I will show you a library which I developed during my BTech. Okay, that's very helpful for implementing real world, like reinforcement learning algorithms. Okay, so you don't have to go like build. So you can, anyway, you can kind of code your own game environments, right? But this kind of gives you a kind of universal this OpenAI gym like environment. So there is a well-known library called OpenAI gym. Okay, so which is used to simulate game environments. For example, if I want a walking robot, right? So it is hard to build a kind of real world prototype. Instead, the algorithms are tested in simulation most of the time. Okay, so similarly, so I will kind of describe a similar library for grid worlds. Okay, so you can think of it as a maze game. Okay, and later on we will try to learn some theoretical like concept like value iteration, policy iteration, and see how we can implement them in Python. Okay, and in the course, I guess the maximum that is covered is TD learning, so it's part of model free reinforcement. Okay, so we'll touch on model free reinforcement a bit. Okay, there are kind of quite a bit theory before it to understand how this model free reinforcement work. Okay, so okay, let's dig in. So uh, like kind of get help of the material, right? Like I am kind of using slides from Emma Brunskill from like Stanford. Okay, Professor Emma Brunskill's slides. So that kind of gives you a good starting point of, like, if you are novice in reinforcements, and her slides and her YouTube videos. So you can, so the YouTube video link is also available in the slide here. Okay, the playlist, entire playlist, as well as the course material. So if you want to dig deeper, you can go check it out. Okay. But anyway, what like up to TD learning, whatever is covered in the course, I will kind of touch upon all the theoretical concepts from that up to that part. Okay. So let's start. So I guess this is already I explained yesterday, right? That so the concept of reinforcement is there is an agent uh, that take action on the environment. The environment change its state to the next state, st plus one, and the agent take action based on the current state it observed. Okay, so the kind of loop is st, at, rt, st plus 1. So you observe a state, you take an action, you get a reward for that action, and then you transition to a next state. Okay, and then it continues until you reach a terminal state. So you start from a starting state and then end on a terminal state, S capital T, for example. And terminal state can be defined as where the game end. So it can be because the agent died, for example, the agent fall into a pit, right? So that can be a terminal state, or the life of the agent is ended. Okay, let's say the agent has an age limit, right? So it can only be live until, let's say, 20 seconds. After 20 seconds, whatever the state will be, that will be my ending state, okay, or the terminal state. So this loop is, sometimes there can be infinitely long these playing sequences, right? So if the agent doesn't have any age limit, or if the agent, if there is no kind of adversaries to the agent, then this interaction may go on forever. Okay, however, in game like scenarios, we always content the time span, how much the agent can play at max, how much the agent can play, okay, or take action in the environment. So this is the kind of reinforcement loop. Okay, and why I'm saying reinforcement loop, because based on this reward, that's the reinforcement signal. Okay, so based on the reward, the agent kind of optimize its actions. So it reinforces good actions, it penalizes bad actions, okay, in a particular state. Okay, get the point, right? So why it is a reinforcement learning loop? Because based on this reward signal, my actions get reinforced or penalized. Okay, so whatever works earlier, I will reinforce that action. I will increase the probability of taking that action in a similar state, and whatever that didn't work earlier, I will reduce its probability of taking that action in a similar state. Okay, that's why it's kind of called as a reinforcement. As the agent learns how to kind of tap into this reward signal to improve the actions. Okay, now let's go to the these things. So I will refer to few material. Okay, so this is one material I will refer. This is my notes from bachelor's, and some parts from here also. Okay, so this is Professor Emma skills slides. Let's see. These are not important. These are yeah. So what is, like, how you can define it? So learning through experience or data to make good decisions under uncertainty. This is the definition of reinforcement learning. So what are the key points? So we are learning through experience slash data, right? And what we are learning to take good decisions under uncertainty, means that that decision kind of gives you a probabilistic view of the next state. Okay, so basically, so it's not always guaranteed that taking that action would always benefit. It's kind of an uncertain environment. Okay, still on average you are trying to do good. Okay, so taking the same actions might not work, but most of the time that action is fruitful. That's what you are learning. So you are learning at which state what action would be most probable to have good rewards or good returns from that point. Okay, and you are learning it through by experience, or by, if you have lot of data, right? So let's say I have lot of let's say data of a particular event like racing. For example, if I have sensor data of race cars, right, I can, and then let's say the steering wheel look position and all. So I can train a model to do better in race in car race based on the data too. I don't have to go and collect real world experience. Okay. So three things are from like, so did I record? Yeah, I record. Okay, fine. So the main 3 points are either I'm learning from experience or data, I'm learning to make good decisions, and the world is uncertain. Okay. And this is how we also learn, right? So we are learning from experience and data. Let's say, what is data in our case? So either we experience ourselves or we see uh, like experience from others, right? You also consult to people. That is what data means in this case. So for example, let's say you want to take some course in your college, right? You'd go and talk to your seniors, right? Whether that course is good or bad, whether the instructor is good or bad, or whether he explains it properly, like something like this. So this is what data means. So based on that data, you don't go and experience and then take decision, right? Because you have to take decision before experiencing it, whether I should take the course or not. So what you go, you collect data from other people, and then based on that data, you try to make a decision. Okay. So it's basically, so the theory of reinforcement learning is like directly aligned to how we take actions, and the algorithms are also very. So later on, if you get time, if you just look like dig into the algorithms for reinforcement learning, you see that the kind of philosophy behind all the algorithms are very much similar to how we take actions or how we think before taking some decision or doing something. Okay. Now this is fine. Yeah. uh, these are some examples. For example, so the algorithms can outperform humans in board games when there are, like, let's say, a lot of branching like next state probabilities, right? For example, here it is Go. So in Go, the next states are like very, very big. Okay. So this, for example, the entire duration of the game, there are like lot of combinations that can be possible. Okay. So in our human brain, it is not feasible to remember all those combinations, right? Or devise a policy or some mechanism by which we can interact with Go that is optimal for all possible states, right? But because of the this nature of this reinforcement learning algorithms, it can outperform human performance in board games. This is kind of an example scenario. Okay, so it happens. So this AlphaGo, right? AlphaGo model is there that outperforms the best Go player in the world. So it's like these are another example. So how to control yeah, some kind of machinery. Okay. Yeah. So this is some medical applications of COVID testing or something. These are not that much important. Okay. So GPT also have a human in the loop reinforcement learning part. Okay. So GPT also kind of reinforces the 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 answers which are better, or let's say you are marking this answer is correct or wrong, right? Based on that reward signal, uh, GPT also kind of optimizes his answers. So that's also reinforcement learning. Okay. So there is this reinforcement learning part of GPT that optimizes itself based on how user interact with him. Okay. Yeah. And so over the years there have been huge interest. So this is the, I guess, the number of paper or article published in this domain. Okay. And I guess this is something don't need to know. Mm, yeah. So these are kind of the motivation of reinforcement. Okay. So not required. Yeah. So see, what reinforcement is kind of, so what learning means in case of reinforcement learning, right? So we are optimizing it first of all, and we are optimizing it for delayed consequences. So I may take an action now which has a kind of delayed impact. Okay, so for example, I can like choose to not wear a shoe that may result in a kind of leg cramp later on, right? So kind of something like this. So you choose or you decide something that has a future impact, not immediate impact. Okay, so by taking some actions, you might end up in a state in future that is bad. That is not like, let's say it's not bad immediately, and you kind of think of many scenarios, right? So for example, in chess, right, you might take some your let's say your starting move was or opening move was so bad that you are in a bad state after you don't realize it at that point, but after some moves, that initial bad move has put you in a position which is bad, right? So similar things. So your actions has a delayed consequences, and you explore also. So it's not like you exploit all the time. Okay, exploit, explore. This is kind of an terminology that we'll be using a lot. Okay, so explore means you will try new actions or new options, whereas exploit means okay, um, option A works all the time, so I'll take option A. But see, when I don't know anything about the system, right? When I don't know anything about the environment, I cannot, I don't have the privilege of knowing which action works, which action doesn't work, right? So initially, my agent should be exploring a lot. So my agent should be taking all possible actions and validating which actions work, which action doesn't work, right? After some time, after uh, let's say after a like enough amount of trial and error, right, it should reduce its exploration and start exploiting, right? It should start your like, okay, now I know that option C works fine, so I will go with option C next time if I see a similar state. Okay, so your exploration and exploitation, those two kind of gives you a general solution. So generalization means your model would work um, even after some minor changes happen on the environment. Okay, so you explore and exploit. So basically in the first half of learning you explore, and then after you have a good amount of data you start exploiting. Okay, still explore a bit because you want to kind of gather information about untraversed states, right? Let's say you haven't traversed a part of the state space, a part of the game, right? And now somehow with some uncertainty you have reached there, so you would also have some small amount of exploration there, right, to better understand that part's dynamics, right? And that by like kind of uh, like judiciously choosing between exploration and exploitation, you kind of have a generalized solution. So these are the learning targets. So you optimize for delayed consequences, you explore also, and you kind of give us a generalized solution. Okay, that works well for all possible states or all like probable states. Okay, so maybe some states are some like reaching to some state is so low probable that you don't care, right? So that doesn't count in this case. So all probable state have a good enough solution. That's what means generalization. Okay. Okay, so these, I guess we have already talked about. Okay. Yeah, these are not important. No, so this is, I guess you already know that the agent take action, observe the world, and these loops goes on. And the goal is to select actions that maximize total expected future rewards. Okay, so total expected future rewards. This is something new. So how we do know future rewards? You can know the next reward, right? Okay, I take some action. I know the next what would happen. That's what I know. That's what immediate reward mean. Now, how would I know future reward? So that's the bit tricky part. So for example, what we do, we basically take some action and kind of hope that okay, these things will happen, and now after 2 days I would be in a good position, right? Something like this. That's what called planning, right? You plan ahead and then take action. So that is what is total expected future reward. Okay, so if you, let's say, plan, and after planning you kind of thought that okay, now this way I might lose, then you'll not take action, right? Not take that action. Instead, you take some action which will, let's say, have a better future expected total reward than that action in which you lose, right? So our goal is to maximize the total expected future reward, and yeah, may require balancing between intermediate, like immediate and long term rewards. So maybe I'm greedy, right? If I am greedy, so I will only see what will happen in next 5 minutes, right? Let's say I'm not greedy, I am kind of an intellectual person, then I will think properly and kind of think in a long term way, right? So if I take this action, it might have immediate, it might not have immediate return or immediate reward. I might not get something out from the decision in next 5 minutes, but in 5 years it will be fruitful. Okay, so that's what is called balancing between immediate and long-term rewards. So future, how much future you want to see? So if I am too greedy, I will just see next 2 minutes, right? Up next 1 minute, what is my reward? That's what I'm optimizing. I'm optimizing my next 1 minute reward when I'm completely greedy, right? Now, when I'm a bit well thought, then I'm optimizing for, let's say, next 10-year rewards, right? Yeah. So that's what we are optimizing by this. Okay, these are examples like what can be reward functions, right? For example, a camera in the kitchen, right? And you are kind of using a dishwasher robot. So in that case, my reward will be okay, +1 if no dishes are on the counter. Okay, otherwise you just move joint. So your target is to so otherwise you are getting a -1 or 0, right? So if there are any dishes on the counter, then you don't get a reward. If there are none, then you get a reward. So your objective would be to quickly finish up all the dishes. That's the objective of a dishwasher robot. Okay, so these are kind of is, for example, this is a human loop, right? You observe that your blood pressure is high, so you go exercise and meditate, right? And you then observe again whether your blood pressure has reduced or in a healthy range. If it is reduced, then you get a +1 reward, or you get a -0.05 if there are, let's say, side effects for the meditation or medication, or let's say you have cramps on due to exercise, right? So this is kind of an like real world human scenario where we apply reinforcement, right? So whether if exercising work, then I go for exercise. If, let's say, I go for exercise and then I have leg pain, right? So I go for medication, something like this. So based on what's my reward is, I will kind of either choose exercise or choose medication in a blood pressure scenario, right?
So can you give me some example for reinforcement?
Yeah, these are kind of like real world reinforcement examples. So exactly. So your your blood pressure is high. So either you go exercise or you take medication, right? Yeah. So how you do choose? So if medication works, or if it has, let's say, side effects, say you do, so you go for exercise. Or if exercise doesn't work and you have leg pain, then you go for a medication, right? So it's kind of an uh, like trade-off, what you choose based on how much reward you are getting in long term.
So what type of means machine we are going to create by reinforcement learning?
So see, wait, let me, yeah. So what type of?
Means what type of machine we are going to design with the help of this
Yeah. So,
reinforcement?
so for example, see here we will be, I guess shortly we will be introducing this library. Okay, this Gridworld library that you can play with. See this one. So there is a mouse, okay, and there is this cake, and this grid world you can define on your own. So you can have any kind of structure of walls, but you have to have a valid path to the cake, right? And then you can learn what is the kind of best way to reach this cake. This is the like simplest example that you can code. Okay, so good examples would be, let's say, Mojoko, Mojoko RL environments. This is like really like fascinating stuff. Okay, yeah, something like this. See, you can also try to solve some puzzles, try to kind of have a robot structure work, right? So for example, this cheetah structure, it learns to run as fast as it can, or this ant structure, it also learns to run. But initially, you would see that it is not running, because what you are learning is to put like put how much force on which part of these legs so that it can run, right? So the model is basically learning in which part of the leg I should put how much force so that I can run as fast as I can. So these type of things you can learn uh, with this.
I think we don't have the output for the reinforcement learning
You don't have the.
output.
Uh, I cannot really hear you. Can you write it?
Uh,
Yeah. No, no. So these are not within your not within the course. Okay. These are the examples that I'm giving. So in the course, I guess you have only up till TD learning. Yeah. No. Output is basically your policy in which state you take what action. So output is this one, for example. Your output would be something like this. This signs you can see, right? These signs are your output. So at this state, I will take a right. At this state, I will take a down. At this state, I will take an up to reach this goal, or this to reach this cheesecake. Okay,
So,
so
sir,
this is
my
your
concern
output.
is that now, like in supervised learning, we used to provide the sample data and with the correct output so that it can
Yeah,
judge the means
yeah.
machine is going to judge the things.
Okay.
So that
Now I
in that way, I am asking like in reinforcement learning, we are providing
yeah.
the output or not.
No, no, no. See, in reinforcement learning, the loop is this. So in supervised learning, you are kind of giving supervision, right? Okay, this is the input data and this is the correct output. You learn a mapping, right? Here you don't do that. Here you put the agent in an environment. The agent learn to take correct actions. Wait, correct actions in the environment basically. So and the signal that it gets is the reward. So the supervision that it gets is only the reward signal. So it's something like whether you are correct or whether you are wrong. That's it. Correct or incorrect. That signal it gets, but like what is the output that it has to learn? So what action it should take, that it has to learn. But the only signal that it gets from the environment is the reward. That okay, +1. Thumbs up, thumbs down, this signal that it gets. It doesn't get okay. Um, so if 2 + 3 = 5, so if I'm, let's say, uh, trying to teach agent to sum, right? And it outputs 2 plus 3 equal to 4. I will only give a thumb down. I will not say, okay, no, it will be 5. Right? It should learn that it is 5. If it let's say replies with 5, then I will just only give a thumbs up. Uh, that's the signal it is getting. So there is no labels involved. Okay. For example,
Yes, sir.
yeah. For example, uh, here, right? Here the reward is, here you get a huge reward. You reach the goal state, right? So the reward is, let's say, plus 100. Now in all the other states, you don't get any reward. If you fall into a hole, then you'll get a -1. So your objective would be to reach this state as quickly as possible, right? Or let's say if I also put -1 in the way in all the other states, then your goal would be to reach the cake shortest in a shortest path, right? So that you don't have, let's say, -1 you are getting, right? So you will take the shortest number of, or like less number of steps to the cake, so that you don't have too many minus points. Okay.
Yes, sir. So one thing, sir,
Yeah.
in the final exam,
Yeah.
did we will get the same question which we are giving in our assessment?
No, 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 no. Similar type. And for the reinforcement part, there will be a lot of theoretical questions. So theory is important. So it's implementing the algorithms are not that much important. Okay. So you'll get lot of theoretical questions. What is return? A return like there might be, let's say, four definitions of a return, and then you have to choose the correct one, something like this.
Yes, sir. Like, sir, we have done LDA and all. So, like when we are going to solve the question for LDA, then it will take lots of time to complete that one. So, in that, we are going to get the numeric question or only theory in supervised learning or anyone.
You might have numericals too. Okay, so there could be like, uh, so it would not involve coding as far as I can tell from, see, I emailed um, professor, okay, so the instructor of this course. Uh, Let me see whether he has replied or not. Let me. I emailed him, I guess, 4 or 5 days back. Yeah, Professor Ravindran, right? So I emailed him, and then he didn't reply back yet. So I emailed him to kind of let me know what is the format of the exam paper, but I guess they are not disclosing it. Okay, but from other sources, from talking to my other like colleagues, right, who already took this course earlier, they're saying that it will be mostly MCQs and numericals, not coding questions. So numericals, you can expect, let's say, there are probabilities given for multiple events, and then you have to compute entropy. Okay, or there is a table given, and then you have to compute like, let's say, a decision tree based on that, let's say, 3 or 4 line, 4 row data set. I guess these things you have already practiced, right? So if you have not, just practice these things. Okay, there is a data set given, I can build a decision tree, small decision tree, two level decision tree from it. Okay.
Okay, sir.
Yeah, this
Actually,
type of
sir, I am
numericals should be
getting,
there.
I am facing a lot of challenges while resolving the numericals. So that's why
Yeah,
I was
numericals are
raising
hard.
my concern.
Yeah, numericals are hard after you have this this GMM, HMM. These are really hard to solve, right?
Yes.
Also for the, like, whenever this probability concepts coming, then it becomes uh like bit difficult to solve them. But anyway, practice them. So numericals will be obviously there. I don't think there will be many coding questions at this point. So you can expect numericals, MCQs, and maybe your fill in the blanks. So there can be a small code block, and then you have to fill in blanks some part of it. Okay, for example, there can be questions like this from sklearn dot dash import linear regression. So what is that module that linear regression is in, right? Or let's say this linear regression model is there, and then you are supposed to compute R2 score, right? So what is the code segment that will go there? These things are like pretty intuitive. Okay. So you can either go by elimination method, or if you can remember it, that's fine. Okay, so let's just like get back to our track. So yeah, you got the idea, right? So reinforcement is so there may be questions like you have to connect which example is which type of learning. So now, what is unsupervised learning? What is supervised learning? What is reinforcement learning? That you have to clearly have an idea of it, right? So it can be. So there are already questions in your assignment similar to this, right? So okay, with this example, like which type of learning it is, right? So just get this type of ideas. Okay, so you already know this thing that you take an action at t, you observe the state, and then you get a reward, and then you transition to a next state. Okay, yeah, and then you have this history, right? HT, that is action, observation, reward, dot 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 until the terminal state, right? So this is known as history, HT. Okay, so yeah, so this type of interactions on the world, we can we can kind of think of this world as a Markov process. Okay, so what is Markov? Markov assumption means your history is represented like by the current state. So your history and the current state is same. So that means you don't have to know all the previous states to predict the next state. That's what Markov property means. Okay, or Markov assumption means. This is kind of an like a classic questions that may come. So there may be some 3 options or 4 options. You have to choose which is the correct Markov assumption. Okay, so your history and your current state is kind of equivalent. You don't have to know all the previous states to predict the next state. Okay, that's what Markov is. Markov assumption. Yeah. So this is what the assumption is. So you're given your history and the current action, you can predict the next state. Also, this is equivalent to given your current state and your action, you can predict the next state. Okay. Yeah. So why it is popular? Because these are like kind of uh, like your kind of standard assumption that you also make in a game, right? You don't have to know all the actions you have took earlier or all the states you have visited earlier. You take action based on your current state and your possible choices of actions, right? So it's kind of an assumption that holds on game environments, but not in real environments. So not in, let's say, in real world environments, previous states and actions also matter, right? So the history matters in real world, but for game environments, my current state can kind of represent what actions I can do, can like my planning for the next state, right? It's not always dependent on the history, and it's widely true for game environment. That's why it's popular. Okay, so yeah, so this is an example. For example, so the Land Rover. Um, so it might, let's say it starts at S4 and then it has to reach to S7, right? So it will take a right move to go to S7. Okay, so you can build a kind of model of this world and learn this policy. Yeah, so these are I will explain. Control. Okay, so these Markov processes are kind of like 1, 2, 3. three types. Okay, Markov process, Markov reward process, and decision process. And we already covered Markov process and reward process in the previous week. So what are these? Just for a quick reminder, Markov processes are like gases which only change their state without influence of external entity or without emitting any let's say reward or anything. So those basically change states. So from S1 it will transition to S2. From S2 it will transition to S3. That's what Markov processes mean. So the only thing that is necessary is this transition probabilities, right? So you can think of it as an NFA. Okay, so you can reach to any state with some probability from any state. Okay, so you have to just maintain a matrix of S cross S. So all the rows will be numbered with state numbers and the columns will be also numbered with state numbers, and you have transition probabilities, right? That's constructs Markov processes. Now, Markov reward processes have one extra thing. It doesn't have any action associated with it till now. It only has this reward associated with each state. So after you reach a state, there will be an associated reward. So now there is no action involved, so it transition by its own, right? And only emits reward after you reach a state. And what are decision processes? They are, so now in that case, what is extra? Previously only have transition probability matrix, right? Or transition matrix. Now here you also have a reward matrix. So reward, let's say if it is associated with state, then it is a vector, or if it is associated with state to state transition, right? So from S0 to S1, if you are transitioning, let's say it's -1. If S0 to S2, if you are transitioning, it is, let's say, +2. Okay, so it can be also represented as a matrix, but for simplicity, we can just associate it with a state. So it can be associated with the transition too. So there is a transition matrix as well as a reward matrix / vector based on how you have defined it. Now for Markov decision process, it has actions now. So it's like actually game. Okay, so now you can reach to a state that has a reward. You can take action to move to another state. Okay, so now your probability matrix, transition probability matrix, become S cross A. So at each state, you transition to state A to state B based on an action. So the probability will depend on the action too. Okay, and then you can basically devise like algorithms that gives you the right choices of action to lead you from any state to the goal state. Okay, on MDPs. Now this MDP is basically games. Okay, you can represent games as MDPs. Yeah, so and because of the Markov property, all these things, all these previous three things, and there can be MCQs from this. Okay, so there can be MCQs like 3 definition given, and then you have to mark which one is MDP, right? Definition for MDP or MRP or MP. Yeah. So what are those? So this is this Markov process, right? This or Markov chain. It's like it's used interchangeably. So these are basically sequence of random states with Markov property. So that means it's a memoryless random process. And definition is it has a finite number of states, finite number of possible states, right? And the P is the dynamic or transition model. Okay, so it basically transition from S to ST plus 1, ST to ST plus 1. Now this is the kind of transition probability matrix that I was talking about, that all the rows will be marked with states and the columns will be also marked with states. So S1 to S1, S2 to S1, Sn to S1, and then from S1 to S2, S2 to S2, something like this. Okay. Yeah. So this is kind of the like this Mars rover example, that okay, if this is my model, then yeah, this is the transition probability matrix. See, from S1 to S2, the probability is 0.4. So from S1 to S2, S1 to S2, 0.4, right? And see, from S1 to S1, there is a self loop. So its probability is 0.6, right? So it can loop to the same state with 0.6 probability. Okay. Yeah, you might also have some kind of this type of diagram, and you have to choose which matrix is the correct transition matrix. Yeah. Now, if you sample from this, right? If I, let's say, put my mask over here and then I sample, right? I just see for few observations which states are getting transitioned. So I can have these type of transitions. So from S4, if I start from S4, I can move to S5, I can move to X6, and then I can move to S7, and then just I loop 3 times at S7, and then go like that kind of goes on and on, right? Until you reach a terminal state, or it can be an infinite chain also. Yeah, so the definition is it has a finite number of state of a reward process. Like this was Markov chain or Markov process. It doesn't have any reward, doesn't have any action. Now Markov reward process is it has same. Only one thing added is the reward one that I already told, right? So your state is finite, your dynamics is there. So there is this state to state dynamics, and there is no action yet. The current state is only dependent on the current, like the next state is only dependent on the current state. Okay. And then you have a reward function that is RT at a state S. Okay. Yeah. So this is basically a reward function that you get based on the state. Okay. Or see, you can also think of this expectation of ST given S given RT. That means your your rewards are basically associated with the transition. So you can reach from ST, you can reach to, let's say, S1, S2, S3, right? And by reaching these three states, you might have uh, like different rewards, right? So from ST, you just take kind of average of all the rewards. That's what this means. Or you can associate it with kind of a state also. That okay, my particular state has a particular reward. And also it has a discount factor. So discount. So because it has a reward now, you can kind of think of long-term, short-term rewards, right? So discount factor is that thing. So a high discount, so its value is 0 to 1. So a high discount factor means it will uh, look look further in future, whereas a low discount factor means it will look like greedily. It will not look far in future. It is kind of a short-sighted model. And why it is important, like in next two slides you will see. So if my discount factor is 0, that means I am only seeing the next reward. If my discount factor is 1, I am basically seeing all the possible rewards, all the rewards from one state. So I'll see the concept of value is there, and there are no actions. Okay. Yeah. So see, this type of thing is a kind of Markov reward process. So now each state has a reward. So reward is +1 in S1, +10 in S7, or 0 otherwise. So only this state has a +1, this state has a +10, and then all the other state has 0 rewards. The transition probability, everything is same as the Markov process. Only the reward is added to the states. Now why it is important? See, return. So this concept of return is, let's say, what is return? So you put some kind of, so return is what? Return on investment. You know this term, right? So you invest something and then you expect that, okay, after the end of 2 years, I would have this much return from it, right? So this much added benefit. So that's basically the reward, right? How much added benefit you have, that's the reward. So you basically go, so instead of looking into immediate gains, you look for a like kind of future gains, right? So return is the exact same concept. So return at a particular state st is rt, that return plus rt plus 1 plus rt plus 2 plus rt plus 3. So for example, if I took gamma equal to 1, right here, that's the discount factor we are talking about. If I just take gamma equal to 1, it's basically rt plus 1, rt plus 2 till you get the terminal state, right? Or here it's known as horizon. So horizon can be infinite as well as terminal. Let's just take it as a terminal state. So you just take all the rewards from that state to the terminal state. That's your return, GT, at that state. So GTST is equal to RT plus 1 plus RT plus 2 plus dot 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 R capital T. Okay. Now, why this gamma is here? See, if I have a number gamma which is within 0 to 1, and if I square it, cube it, or let's say like, just keep on, right? Like gamma to the power 4, gamma to the power 5, all those things. The gamma basically reduce in an exponential way, right? It kind of reduce like this curve. So it becomes kind of very close to 0 after few powers, right? So let's say if I put gamma 0.9, right? Then after let's say 20, gamma to the power 20, it becomes very close to 0, right? As see this gamma is like multiplied with the current, with the reward associated with it, right? Say for example in the second step, so here in the next like immediate next state, it is gamma t plus 1. In the next one, it is gamma to the power 2 t plus 2, something like this, right? So the gamma controls how far you will kind of foresee. So if I put gamma to be 0.9, then I can foresee up to, so theoretically I can foresee up to 10 future steps. Okay, so the equation that is used is 1 by 1 minus gamma. Okay, that's the kind of number of states I am foreseeing, like statistically. So this can also be asked. So the theory is, after you have I guess 1 over e decay of that card, right? 1 over e decay, then you at that point you are kind of bounded. So 1 over e decay is happening at 10th step at 0.9. So the equation is 1 over 1 minus gamma. That is how many steps you are foreseeing for GT. Okay, so if I put gamma to be 0.5, right? That and it becomes 1 over 1 minus 0.5, it's 2, right? So you are only foreseeing 2 states. So until here, this will be kind of significant. Then beyond this point, those will kind of gradually decrease, like quickly decrease, not gradually, so like rapidly decrease to 0. Okay. Yeah. So if I put gamma to be 0, then I am just only taking RT, the current keyword, not anything. I'm not forcing anything. I'm completely greedy. If I put gamma equal to 1, then it becomes like till the terminal state. I'm looking till the end of time, or till the agent die, right? Till the lifespan of the agent ended. Okay, at a particular state. Okay, so you can think of return, and this is like very crucial theoretical concept. You can think of return something like buying a land, right? So what do you think? You or let's say building a house. What is the kind of thought process in your mind, right? So when I will retire, this is where I will come and live. Something like this type of thought process comes, right? So at this state, whether I should build a house or not, let's say I have the land, right? Current state, I have the land, I have the money, I want to build a house or not. Uh, what do I see? I see, okay, now in future I will grow old, I will retire, then I will come and stay here till the end of my career, right? That's the terminal state. Okay. So I see all the possible rewards, kind of estimate all the possible rewards still there, and then I choose, and then I kind of decide whether I should build house here or I should not build house here. Later on, I can just sell this property, build a house in like any other place, like this. Okay, so GT is the same concept. Now, see, this can vary, right? So for me, GT at a particular state can be very much different from you, right? Now, if I want to have generalizability, right? If I want to like kind of study the value of the state of having a land and then the resources to build a house, I have to see multiple people's choices, right? Whether all the peoples that are kind of in like in let's say within my observation, what they are doing or what the kind of average return they are getting, right? So you also take into account other people's kind of experiences on this, right? Same thing. So if I want a kind of statistically significant uh, metric for validating whether I should, like whether this state is good or bad, right? Then I go for average returns. And see here I am not talking about action. It's only yielding rewards. So think of that your actions are predefined, right? So for example, your actions are, let's say, decided by some entity. For example, your parents, right? Then or any other entity, right? Your actions are already decided. Now you see whether I'm in a good state or a bad state. What do you see? You see you see whether, let's say, yeah, other people have what other people have get returned from this, and then you just take an average, right? So that's what value function is. So value function is expectation is average, like statistical average. Okay, so average of return given this state. So there can be multiple possible returns from a state, and then you just take an average of the returns. That's what value function is. Okay, and these are like very common in kind of MCQs. Okay, so discount factor, you already know that. Okay, if it is equal to 1, then I'm just looking foresee the entire future. If it is less than 1, then I can just bounding my view, right, up till certain states. So if it is 0.9, then I'm just foreseeing 10 future states. Yeah, these are kind of mathematical things. Okay, now this is like quite a jump. So let me show you how this comes. Okay, or maybe it is there somewhere. No, it's not there. Yeah. So how I can write this equation from this. Let me just connect it on which pattern. Okay. And here what dynamic programming comes in reinforcement. Okay. Now let's choose the black one. So our equation is GT return is nothing but RT at a particular state, obviously, right? And the state, let's say the state transition is like this: S0, you transition to S1, and then you transition to S2 dot dot dot, somewhere in the middle of the entire experience, you are transitioning to ST, right? And then you transition to some other state, dot, dot, dot. And let's just put ST plus 1. Then you transition to ST plus 1. And then again you transition, and then you, at the end you transition to ST or terminal state, right? So your definition of return at this state is what? You get rewards like this, right? At you get R0 here, R1 here, R2 here, RT, RT plus 1. Here you get R capital T. Okay. Now return at this state is RT plus RT plus 1 plus T plus 2 plus dot 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 plus R capital T. Now, why gamma come into picture? Just to bound this, right? So if I only want to take 10 future steps, right? Then I just multiply it with something within 0 to 1, gamma to the power see T plus 1. So let's just keep it T, okay, just for simplicity, but there is a mathematical term for this. So if it is capital T, right, then it will be how much? So T plus 1, it is 1, right? So here I can write T plus 1 minus T, right? And then it becomes 1. Yeah, so here I have to write T plus 1 minus capital T minus small t. That would be the correct mathematically correct form. Okay, so this is how you multiplied this thing with gamma within, let's say, 0 to 1. Or it's touching, so it's third bracket. So it can be 0 or 1, not only within. Now value function, you and see, these are very very interesting stuff, right? So you're basically getting an average. So see why you can get multiple returns from a state. See here in the top we have only considered one trajectory, right? So now you can also have something like this. Some from ST we are considering, not S0, ST. You can transition to, let's not say ST plus 1, right? We can say ST plus 1. One thing you can transition to. Again, you can also transition to ST plus 1 prime, right? You can also transition to ST plus 1 double prime or any other states, right? Any other possible states. Yeah, you can transition to, let's say, all possible reachable state from ST. Okay, and then you can, again, you have a trajectory here, you have another trajectory here, all possible trajectories, right? You can have another trajectory break from here too. So ST plus 2, ST plus 2 double prime, right? So there can be like hell lot of possible trajectories, right, from ST. So this is just one example that we took. So you can, let's say, in one example you can sample. So in one example, you can sample this trajectory. In another, let's say another sampling event, you can sample this trajectory, right? So that means, and the rewards, associated rewards for these trajectories are different, right? So basically, you would have a sorry. Yeah, you would have a GT here. You would have a GT prime here. You would have a GT double prime here, right? So what you took, so from this to this transition probability, you know, So let's say the transition probability from here to here is let's say 0.3, right? And here it is 0.2, remaining is here 0.5. Okay, so what you take, you just take a probabilistic average. So probabilistic average is known as expectation. So that's why you write VT as expectation of GT over particular state ST, given a particular state ST. So from ST, you can transition to many other states, right? Many other possible states. So you just take an average of the possible GTs. So in here, it will be something like this. 0.3 times GT plus 0.2 times GT prime plus 0.5 times GT double prime. So this is what I mean by probabilistic average. Okay. Now see. Now it becomes interesting. See. Now I can do a recursion here. So VT is equal to, if I just take expectation, let me just go back to that equation. Yeah, see, you are getting a reward here, right? You are getting a reward here, R1, or let's say RT, and the rewards are associated with states now. Okay, because we are only looking into Markov reward processes. So each state has a possible reward. So RT, and then you whatever you transition to, that becomes RT plus 1 or RT plus 1 prime. Here you would have RT plus 2, sorry, 1 double prime. And this thing can kind of forward, right? Here also you would have an RT plus 2, RT plus 2 dash, and there's a double dash, triple dash, 4 dash, something like this, right? Possible rewards at the next transition. Okay. So see, now what I can write. Yeah. So the current reward is fixed. Current reward, I know that I am at state 0. So my current reward is fixed. It is RT. Then plus where I will transition to, and then what will be my return at that point, right? Expected return. So basically, where I will transition to, so I can transition to ST plus 1. So my return at ST plus 1, next return, right? Next return here, from here if I compute, it will be GT plus 1. From here if I compute, it will be GT plus 1 prime, and from here it will be GT plus 1 double prime, right? And it based on the transition probability, right? So basically you are 0.3 times GT plus 1 plus 0.3 times. So, and not DT. So see here, GT can be also different, right? So basically you are, let me rewrite this. So from here also you can have multiple GTs sampled, right? Because there can be two possible, multiple possible transitions that are possible. So for each line, so for let's say, if I from here, if I took this route, there is a possible GT plus 1. If I took this route, there is a possible GT plus 1, right? So you just took expectation or average, probabilistic average, right? So the actual equation would be 0.3 times expectation of GT given ST sorry, GT plus 1 plus sorry, yeah, take an average, right, plus 0.2 times expectation of GT plus 1 prime given ST plus 1 T plus 1 again into is plus again probabilistic 0.5 probability I can transition to this state times expectation. So from this entire loop I can have expectation of GT plus 1 prime given ST plus 1. And see, these all of them are right. We can replace them with V of ST plus 1. Right? Basically V of ST plus 1. Right? Here also we can represent as V of ST plus 1. So value of the next state can be replaced in all the positions. And what is this? This is basically expectation of the value of next state, right? So that means, and this basically you can represent it as PV. Okay, so P is the transition, and that's basically mean expectation of V. So we can just write TV is equal to RT plus expectation of VT, T plus 1, right? And we see you can just introduce gamma here, right? Just to discount it, you can just introduce gamma. So next step, I am just discounting it by the gamma factor. So I will just only take 90% from the next onwards. See, this entire thing gives you kind of a good recursion, right? Good recursion. And this EVT plus 1, we can just expand it just to put it in the form. We can just expand it as like this. VT is equal to at T plus here gamma P VT plus 1. PV means the expectation. P is the transition probability matrix that gives you these probabilities. Okay, so see, this is what the equation is here, right? See, exactly. So summation of P V S prime, right? Okay, so yeah, so what does it mean? It is the value of each state is equal to reward plus the gamma discounted of the next state probabilistic values, right? Yeah, sum of future rewards, discounted sum of future rewards. So by this, you can actually tell which state is good or which state is bad. So if you know, and this is a kind of a dynamic programming equation, right? So you put this V initialized to 0 first, and then you know the transition probability dynamics, you know the you know the reward dynamics, right? And you took a gamma value. Let's just keep it to 1, let's say 1, right? And then you can just apply this equation multiple times until this VS converge. So VS converge, you can just take, let's say, infinite norm, right? You just minus the previous VS value, the current VS value, and then just take infinite norm. So infinite norm is nothing but max of that minus. Okay. So if that infinite norm is less than some epsilon value, you just stop there. So that's when you know that my value has converged. Okay, so just by using a kind of convergence loop, initializing VS to 0 at the beginning, or let's say two random values at the beginning, you can kind of evaluate which state is good or which state is bad in a Markov reward process. Okay, so and I'm not saying immediate good or bad. You can estimate whether it is good or bad in long term. So in long term, you can think of it as a long term. Okay, so if I'm at this state, in next 10 steps, if I put gamma to be 0.9, in next 10 step, how much average reward I can expect. That's what this value function means. Okay. Yeah, and you can also like implement the same thing in a kind of matrix multiplication fashion. So you can like this summation can be directly replaced with a matrix multiplication operation, right? Just yeah, that's what matrix multiplication is. Yeah, here, right? You just multiply the P matrix with the V matrix that would kind of give you that summation of PS1, VS1, and then you just sum it with reverse. So you just apply the equation for all the value states. Okay. Yeah. So see, this has a kind of good um, this thing, right? So you can just put this part to the left side, get V as common, and then just do a inverse multiplication, right? So there is a closed form too. So you can just have P instead of that recursion, instead of this that dynamic programming, you can also apply a closed form like this. It's very common. So it's like put the left V part to the left side, take V as common and just multiply it with an inverse of the left side. Okay. So this is kind of an analytical solution. Okay. And so this is actually known as policy evaluation. It's like later on we'll discuss. Yeah, and the complexity for multiplying or taking inverse of a matrix is open cube. So it's very bad. So it's complexity wise, the computing value function of a Markov reward process is very bad. Okay. Yeah. So okay. Yeah, we can check. Do you want to do a coding example on this? So just to so previously we have already defined a Markov reward process in the last class, right? So you can just use this equation to verify. Let me quickly do that so that you get an idea that how it is different from the reward function and the code 9. I know that this theory is bit a kind of the first time you hear it, it's not kind of tractable. Okay, but like more and more you hear these things, he is kind of settled down a little bit. Okay, so I would like strongly suggest go and watch the lectures of Brun skill if you want to improve on this reinforcement learning topic. Let's delete all this. Yeah, and I started during my third year of BTech. Okay, so it takes long time to kind of grasp these concepts and implement reinforcement algorithm from scratch. Okay, so just if you want to do research on this topic or if you want to learn more, you just start early, I would say. Okay, so we have already defined a Markov reward process. Yeah, this is the reward matrix and this is the transition matrix. Okay, just copy it. Yeah, and just to verify what are the shapes. So this is again S cross S. This is column vector, and this is column vector 2, and this is column vector. Okay. So this one you have to do a column vector. Okay. Now we have a column vector. We have this. Let's put gamma to be 0.9. Okay. So basically we are observing till the next 10 steps. And the equation is 1 divided by 1 minus gamma. compute how many steps you are looking foreseeing basically. Okay, now what is the equation for this? V is equal to I means identity minus gamma p inverse r. Okay, so you can just so let's write it. V is equal to I minus gamma p inverse r. This is, yeah, and you just put it this one, right? Okay, so I means np. So this is a 3 cross 3 matrix. So np dot EYE is it? np dot linear. Oh, sorry, we don't have numpy. np dot EYE. This would give you a yeah, 3 cross 3. So 3 cross 3. Yeah, it gives you an identity matrix. Okay, so minus p, we already have 3 cross 3, so gamma times p s x s x s. So that's how you know that, okay, it's a MRP. It doesn't have accents. If it is an MDP, then it will have an accent field too. Okay. Okay. Now inverse, how you can do it? Dot I, or you can yeah, dot I would prefer. Okay, dot I. Uh, okay, so now I have to cast it to matrix. So now let's just not use dot I. np dot linear L dot inv, that I can use. It gives you an inverse. Okay. Yeah, compute the multiplicative inverse of matrix. Fine. So into the R, right? Comma R, and then just you do an np dot matman. Yeah, so this is the value function. This is the value function. Assign value. So see how much it is different from the reward function, right? So the first state has reward of -1. The next state has reward of 10, and last state has reward of 2, right? But here you see the first state has a return or average return for next 10 steps, right? 10 steps to be 25 for the, yeah, but for this state it is 34, and the last state it is 28, right? So let's just tune gamma a bit. Let's put gamma to be 0.5, or put gamma to be 0, right? So by theory it should be only looking at the next reward, so immediate reward, right? So it should be same as the reward function, right? Run, see that its value function is same as the reward function. If I put gamma to be 1, then it's basically seeing the entire horizon, so until infinity. Okay, so it should be, yeah, see, it's a very big value, right? Very big number, e to the power 18. Now if I put 0.2, a 0.5, that means I'm only looking into next 2 steps. Okay, so yeah, it's kind of similar to the reward function, right? 12, 5, and this. Yeah, you got the idea, right? So basically value gives you a kind of foreseen reward that from each state based on the gamma. Okay, I guess it's clear. These already you know. See, okay, so this is the kind of entire kind of the realm of reinforcement learning. Okay, these are the kind of algorithms there. So what you are currently learning is this model based, this part model based. Okay, so you are currently learning to build this model of the environment. So MDP, MRP, MP, these are basically model of the environments. Okay, now with this you can have model based algorithms, like there are algorithms named as policy iteration, value iteration, policy evaluation, right? So those basically give you the sequence of actions that you can take from all the states. Optimal actions that you can take from all the states. Those are known as model-based reinforcement learning algorithms. Now there can be model free. So model free is, what is model free? You don't have to know the transition probability matrix. You don't have to know the reward matrix, which is very hard to get in real world basically. So you can build a game simulator, but it is very hard to get hold of these matrices unless it's a like maze world, like maze or something similar, simple, right? So if you have, let's say, a robot walking game, right? Then you cannot build this PNR, right? It's very hard to build this transition probability and reward matrix. Rather, you can define the reward as a function of whether you have gone to the next state or not. So you can define reward easily, but you cannot define reward for each and every possible state, because state can be infinite, right? Possible states can be infinite. But for a simple world, like let's say this grid world, right? Where is it? Yeah, the grid world here. Simple world like here, right? You can, there is finite number of states. Like for example, here maybe it's like 60 states, 60 states, and you can define reward at each state. So for example, I can define, okay, there is a -1 if you fall from a hole, right? Yeah, if you reach here, it's a +10. So I can define. So here, getting hold of this P matrix, and the P matrix R matrix is like, okay, if I take right action here, I'll end up here. If I take a down action here, I will end up here. That's what this P is, right? This transition probability matrix is. So defining those two things for a simple case is very easy, but for a complex game, it is not easy. So in that case, it's easy to sample the world, not get that those kind of models. Okay, so you can sample the world efficiently. You can just go and play for some time, and then based on the experience, you try to learn. So those are model free. Okay, and I guess there is like TD learning is a model free method. So you have some part of TD learning in your syllabus, and then there are kind of mix of both worlds. So there are value based methods. Okay, so the thing that you learned recently, right? So the value, um, your value function, right? So there are methods that optimize the value function. For example, you might have known q learning, right? This is a buzzword few years back, q learning. So q learning comes under this value based reinforcement. Now there are other algorithms that directly try to optimize the policy. So either see, so how you can learn value and policy based reinforcement learning, which is value based, which is policy based. So if I know, let's say if I know how much return I will get from each state for each action, then whichever action has the maximum value associated with it, I will take that action. So basically, if I know the value, policy is basically take whichever has the maximum value, right? So there is a direct conversion from value to policy. So whichever algorithm doesn't consider policy to be directly learnable objective, right? It tries to learn the value function, that is value based approaches. And there are algorithms which tries to learn directly the policy, not the value function, directly which action I should take. Okay, so in that cases, so for example, when the action space is too large, right, then you cannot efficiently learn all possible values together. So then going directly to the action is more efficient. So yeah, so those are kind of policy based algorithms. And example is PPO, TRPO, something like this. Okay, and in middle there are algorithms which consider a value based model as well as the policy based model. Those are known as actor critics. So the actor is the policy network that takes action directly, and the critic basically try to evaluate, okay, whatever action you took, what is the value of that? Okay, those are known as actor critic network. So there is this actor which is policy based, and the critic which is value based, and they try to kind of co-learn. Okay, so they try to improve both, like simultaneously they try to learn each other, like the dynamics of the world. Okay, so this is the entire space of reinforcement learning. So I guess we are only concerned about model based, model free, and this like value based learnings. So up to TD, this is purely value based learning. So policy based learning after you comes after you have this policy gradient theory. So that's you can learn. Obviously, you can go and check out the lectures from Bruce skill. Okay, so this is kind of a master word, and this is what is known as policy. So I'm saying policy again and again, right? So policy is basically in which state you take what action. Okay, so for S1 you take right action, from S2 you take right action, from S3 you take a right action, and let's say for S4 you take a left action. So that's what is, if you define action per state, that is what is meant by policy. Okay, and our goal is to optimize this policy. So in which state I should take what action. So for example, here, right, this is the kind of perfect policy example. See, if I put the mouse here, see, it take right, up, right, up, right, up. So see, if I just put it anywhere, right, if I just put it here, see, left, up, right, up, right. If I just put it here, it's also down, right, up. Got it, right? And see, it's actually avoiding these holes. So it's not saying that go right at this stage, right? If I go right, I'll just fall into a hole, right? So it's okay, avoid the goal by going up, then right, and then go up. So this is an example of a policy. Okay. Yeah. So you can, so now I can just go and introduce this library. You can just go play with it. Or I should just continue with the theory one. So it's none. Let me see. Yeah, I guess we are done. This. These are okay. Okay. So let's just quickly discuss Markov decision process. Then I will show the library, and you can check it, play with it after the session. Okay. So Markov decision process here as just one addition to the previous one. It is it now has actions. So with the states, finite set of states, finite set of actions, you have a transition probability dynamics which is conditioned on which state and which action. So now the next state transition is not only conditioned on state, it's also conditioned on which action you do. Okay? And the reward function is now also conditioned with the action. So at what state, what action you took, based on that you will get some reward. This count factor is there. So so MDP is defined as this SAPR gamma. This is the kind of parameters it has. Okay. An example could be like this. So yeah, so from action1, see, action1 is what? Action1 is from here S1 to S1, S2 to S1, S3 to S3. I guess action1 is something like down or something, okay? Or left. Action1 is left, action2 is right. Yeah, action1 is left, action2 is right. Okay, so if you take left, then you hit the wall, you come back to S1, right? If you take from S2, if you take left, you reach back to S1, right? And this, see, there is no noise or there is no uncertainty in the environment. It's kind of a deterministic environment at this point. So whatever you took, with 100% probability, you land to the valid state. So for example, S2 you land to S1, S3 you land to S2. See, S3 you land to S2 here, right? Okay. Now policy would be to kind of learn the best So which state, which action is most probable? So which action I should take? That's the policy pi. Okay. Now if I just add the, if I already know the policy, if I already know what policy I would take, then I can just make it an MRP, right? If I just know the policy, then there is no point of taking action. I already know the predefined actions. So I can just convert my MDP to a MRP. See, just by averaging with respect to the policy, right? I'll only take actions that are already defined, right? So there is no point of taking action. You just slice all the kind of rewards and transitions based on the defined actions. So you transfer a MDP to an MRP. See, the transition, the equations are like this. So you just take a probabilistic average with respect to the pi of the reward model. You take a probabilistic average of the transition model with respect to the pi, and you now remove the a component. So earlier the r was s comma a, so now it is only conditioned on pi r. If I follow pi, it's, this is my rs. If I follow pi, this is my s prime s, or the transition for the MRP, right? Now we already know that, okay, I can evaluate which state is good or which state is bad of a MRP. Now I can see, now I can look through all the possible policies and evaluate my MRP, right? Evaluate my, from MDP I convert it to an MRP per policy, and I evaluate evaluate which policy gives me the best value function, right? So I can just, let's say, look. So if there are how many states were there? Yeah. So there are 1, 2, 3, 4, 5, 6, 7 states, and there are two possible actions. So at each state you can take two actions. So there are 2 to the power 7 possible um, mm, possible policies, right? 2 to the power 7. That means how much? 2 to the power 5 is 32. 2 to the power 6 is 64. 128. So in this environment, there are 128 possible policies. Okay, you can just go, like, look through all the policies, get the associated MRP, evaluate the value function, and just order the policies based on the maximum value function. So maximum value function, so you have value function for all the states, right? You just take an average. You just take an average, or you can take a sum, anything, right? So you just order all the policies based on that average value you are seeing per state, and then you have the kind of ordering of policies, right? Whichever policy is the best would have the best value function. So now you can, like, identify which is the best policy. Okay, but it's resource intensive, obviously, because, like, if there are, let's say, 10 states, it becomes 124 possible policies, right? So as your state space increases, looping through all the policies is not a viable solution, right? But you can always do that. Okay, that's called policy iteration. Okay, and the code is implemented. So if you want to see how to write that code, the code is implemented here. Policy iteration here. See what I am doing. I am is it wait, not this one. It's policy iteration, policy evaluation. Yeah, here. uh yeah, this is policy evaluation, but with that dynamic programming approach, you can easily do that with that same I minus gamma p inverse v. Anyway, so here what I am doing, I have a defined policy, and I just happens to be replacing it with random policy. Take random action at random state. Okay, at all state take random action. Okay, I define it as pi, and then I get the MRP of the model. So I get PSS and PR. Sorry, PSS and RS. Okay, and then I just compute this policy evaluation. So the same um, I minus gamma p inverse v, that inverse r, sorry, that equation. You can also implement it as a kind of dynamic programming approach. So this is the dynamic programming one. So you just loop till the previous value function and the current value function has kind of within an epsilon range. Okay. Yeah. So you have the kind of value for that particular policy. Now you can loop through all the possible policies, rank them, and then take the best policy based on the maximum value you get. Okay. And a good policy output would be something like this. So here, yeah, this is the kind of a good policy. Okay. And if you just follow the policies, so one thing I can show you, anyway, these are for deep reinforcement learning, but how it interacts with the world if I just follow with one policy, right? View my channel. Posts. No, not posts. Uh, Shorts. See, these are kind of yeah, this is for DQN, but sorry. See this. So it starts from here. These are all kind of unsafe states. Okay. If you just step into one of them, the agent will die. So it starts from here. It finds the kind of best way to reach here. Okay. And there are kind of sleep in the environment too. So the agent may take right, but with some probability it might land on left. Okay. So there is this sleep thing. So that's why it's not taking the same route again and again. There is this one slight probability of slipping to other states. You get the point, right? So this is what a kind of emergent policy means. So this is the policy that the network or the algorithm learns. Okay. So you get the point. So you can make an NDP and MRP if you know the policy. If the number of possible policies are finite, then you can just, and you have lot of compute resources, then you can just go ahead, loop through all possible policies, get the associated MRP, and rank the policies, take the best one. Then that's how you can find a best policy. Okay. Okay. Now you can, so instead of going to more theory, right, we can just try to implement this one. Let me see. Yeah, let's just try to implement this one. Then it will be uh, more beneficial, I guess. I have that Gridworld here. Import Gridworld, I guess. Yeah, I have the library. Okay, so so this is one of my libraries. Okay, so you can check out this GitHub repository. Yeah, I built it during BTech fourth year. Okay, so you can you can quickly build a kind of read world with this type of notation. So this A is agent, W is one, and this O's are obstacles, and this G is the goal state. Okay, and this sleep means what is the probability of not going to the desired state. So you can have some stochasticity to the environment. So there is this sleep. So if you, even if you try to go left, there is some non-zero probability that you will go end up right. Okay, so let's just copy it from here. Okay, now I will not consider this big of a kind of environment. Then I have lots of possible policies, right? So the policy, so the actions are left, right, actions are left, right, up, down. Okay, and I guess it is numbered as 0, 1, 2, 3. So let's just consider a small world. So www, sorry, www, w, w. So the two states, I guess, only one, two. And let's say there is this obstacle here, w, w, this goal here, and then the walls. So how many states are there? Possible states? One, two, one, two. No, this is not a state. It's an obstacle, right? So one, two, three, three states. But let's say the agent starts at here. So only valid states are one and two, not the not the last one, I guess. Yeah, not the last one. So you are not considering these states, and you are not considering the last one. So this is one state, this is one state, two states, only two possible states. If I just, and let's just keep slip to be 0 for now. So it's a complete deterministic world. Okay. No, sorry. Play as human. So this is the kind of, yeah. So this is my world. See, you can see, I guess, right? So this is this spike there. If I go there, my my mouse died. Or if I go down and then go left, right? So my optimal policy should be go down, go right, right? So down, right. Any other policy doesn't really gets you to the goal state. Okay. Yeah, why it doesn't close anyway. It's not restart. Close. Okay. Now what are the possible policies you have? So what are the possible actions first? Let's see. Action space environment dot action size is 4, left, right, up, down. So action space, and see this API is the uh, same for other kind of simulators too. So there is this discrete 4 action space, that means 0, 1, 2, 3. Okay. Now action map. See, this is the action map. So 0 means right. Sorry, 0 means right. Uh, 1 means down. So 1 means down. 2 means left. Okay. 3 means up. Sorry, 3 means up, and D means 2. Oh, D means 1. So this is my mapping. Left means 2, R means right means 0, U means like up means 3, and D means 1. Down means 1. Okay. So now I will try to list all the possible policies. So how I can sample a random policy? Let me see. Examples, evaluation. See, this is a valid policy, right? So it's basically list of actions, that you will take per state. Okay, state space. Let's see, env dot state dictionary, right? State dictionary. So this is the state 0, 0, 2, 1, 1, 2, 2, 2. These are the possible states. And yeah, if this is a state that is a whole, this is a state that is reward. See, you can see all the rewards, right? 0, 1, all the rewards, right? So for the first state, the reward is -1. The second state, the reward is -100. So it's that spike. Okay. For the third state, it is the reward is -1. So it's a normal state. And the last one is a goal state. and the reward is 100. Okay, so everything is defined. So how I can define a policy? Let's say pi1, or yeah, pi1 is equal to let's say take left, then take right, then take up, then take down. Sorry, I should 0, 3, 1. This is a valid policy that I have defined. So basically take left, right, up and down at the 4 states. Now I can get as human. Yeah, I can also pass policy here. So it will basically mark my policy. Policy is equal to pi1. See the actions. So yeah, so these two are marked. So I'm taking left at this and up at this state. These two are not marked because these are not somewhere you take action, right? Here you die and here the game end, right? You reach the goal state. Okay. So you see the policy, right? Now I can get the MRP env dot get me see what was the get MRP function. So it is imported from library helper. So from Gridworld dot modules dot no, not from here. So get MRP, you can just go and copy from examples. Like, helper. Yeah, get MRP function, this one. So what it is saying, it is basically slicing all the, so based on the actions, it is slicing the kind of associated rewards and the transition probabilities from the states. Okay. So MRP gives you PSS, PSA from the environment. Get MRP environment, you pass the environment and the policy 1. You get the, what is the error? Okay. So I have to pass an NP arrays. Okay, I now have the PSS and RSS. So PSS, this is the transition matrix because we took slip to be 0, so it's currently completely deterministic, right? And I have also RS. Yeah, this is my RS. And this is like fine. So my current state has -1, next state has -100, 1 and 100, right? Now I can just use this equation to compute the associated value with that policy. Yeah, so this is my, and just take this to be 1, gamma to be, let's say, 1 at this point. If I just do this, what is the error? PSX, no, PSS, and this is RS. RS, so what is the, okay, so it's a 4 state, right? So the I should be 4. 4. Now what is the problem? Singularity matrix, so I have to make it to 0.9. Yeah. So what was the problem? So the problem was with 1, this entire thing is not invertible. So it's the inverse is not, doesn't exist. Okay, so this is my value. See, so what I can take as a metric, just take a mean. And this is my average value for that particular policy. Now, what I told earlier that okay, I can have like all possible all possible policies, right? So let's just write down all possible policies. Go to ChatGPT, ask him to write all possible policies with these actions, 1, 0, 2, 3 actions at each state. So write down all possible combinations of 0, 1, 2. Oh, is it 0, 1, 2, 3? Yes, 0, 1, 2, 3, right? Yeah, 0, 1, 2, 3 for 4 for a for length in P array. So it gives us a code. Anyway, that's fine, no problem. Which are tools I have to import? Yeah, this is my all possible policies. So for the first 0, 0, 0, I'll take right. Okay. Now I will not choose a particular policy. I will just loop through all the policies. Okay. Just make it as a list. Dot to list. Yeah. Now I have list of all possible policies. All fine. I'll remove this. Get MRP is required. Now with this loop, I can just write for I policy I in all possible policies, right? You get the MRP associated with pi I, compute its value function v pi I, right? And then just put in a global list of, and then just take mean, obviously, to get from an array to yeah, from an array to a single value, take mean just, okay. It's not currently required. Okay. So and then put this value to that list. Dot print v5. Now if I run this, what is the error? Oh, list object doesn't have shape. So now for pi equal to, so policy current equal to np dot array pi, and then just replace this with policy current. Where is, what is it? Here, policy current. No, I have the list of all v's. Now let's check which one has the maximum value. We just take max sub v, sub v. This is the maximum value, right? Now see where does it exist. So p dot index 80. It's the 80th combination, right? Now what is the associated policy? This is the associated policy. Okay. So this is the associated policy. Okay. Which has this value. Now see what is it. Yeah, here, see. You take it down here, you take a right here. You take it down, you take a right. You take it down and then take a right. Now, if I want to just play from this policy, right? Play multiple, it will be like not that much interesting. Anyway, you can understand. So from down and right. If I just do a simulation, you can see the mouse will move from here to here. Only that part. It's not that much interesting. So now you know, right? You know how to kind of if the number of policies are finite or tractable, then I can look through all the policies, get the corresponding MRP, evaluate the V, and then just take the policy which has maximum V. That would give me a kind of, it just, yeah, this is the policy. From this state go down, from this state go right. Okay, and if I just plot, right, what is the kind of matplot dot plot as PLT dot plot the V, right? See, this is the kind of all possible policies. If I just go with all possible policies, this is the fluctuation in value function, and the maximum peak, it is around here, right? Around 80. So this is the maximum peak. So the 80th policy, or let's say, what is the policy? Optimal pi, right? This is the policy that MRP has the maximum average value. Now you get the kind of overview of how these algorithms work, right? Okay, any questions? I guess we are out of time. Any questions? So what is still remaining? See, there are ways by which instead of looping through all the policies, you can just go ahead and improve on a initial policy. So for example, you just initialize your policy randomly and then just improve until you converge at some point, until there is no improvement. Okay, that's kind of a way that you can do. So yeah, so these things can be done. So maybe we'll cover it. Okay, and these actually come, if these things come before TD learning. So before TD learning, you have to know. Otherwise, the notion of TD learning is it's it cannot be understood. Okay. Yeah. Anyway, any questions still? So you get all the points that I made.
Hello, sir.
Yeah. Go ahead.
Yes, sir. Good evening, sir. Sir,
Yeah.
actually, I've done my research work. So I want to know which is the most widely now currently trending used policies are now. What is that widely used algorithm?
Yeah. Yeah. What was the questions? So this is the kind of the reinforcement learning is the kind of hottest topic in learning theory, right? In intelligence or AI topic. Yeah. After
Okay, sir.
ChatGPT,
Reinforcement.
obviously. Yeah. After ChatGPT,
Okay,
obviously. So there are a
okay,
lot
sir.
of research that is being done on reinforcement learning now. For example, the how ChatGPT improves, right? By interacting with us. That's also an proximal policy optimization. There is this algorithm named proximal policy optimization. And if you want to see how it is implemented, you can see it from this GitHub repo. I have implemented earlier from scratch. So it is implemented here. Yeah, PPO algo. This is the entire proximal policy optimization algorithm. There is this paper also you can read. So it's kind of the next hot topic after LLMs. Okay, that you can
Okay, sir.
work on in research. Yeah.
Okay, thank you, sir.
Yeah. But anyway, I don't work in reinforcement, by the way. I work in sensing. So yeah, in my research, I work in sensor systems, smart homes like this. Yeah. Okay, guys, I guess you have kind of grasped the entire idea of how MDPs, MRPs are kind of implemented, right? And you can play with this tool, Gridworld tool, if you like. It's very easy to install, and I guess I have did a good job explaining it in the README file, how to install it and all. See, to install it, you have to just copy paste these 4 lines. Okay, and then from the examples, you can just go ahead, copy paste, see some code examples from here, and you'll be able to deal with the library. Okay, and define your own Gridworld environments. So for example, see, if I just define my Gridworld with this, instead of this, I can wait. I just copy from here. Yeah, I can also initialize a Gridworld with a larger environment dot play as human. See, now my world looks like this. So it's very easy. So what I have to do, I have to just have this W means wall, O means obstacle, W means wall, and G means goal, A means agent. So by this, you can create a kind of bounded environment, and then just give it to that grid world function, a grid world object basically. And then you have a thing that you can interact with an agent, or you can get the MRP. So for example, if I want to get the MDP from here, right? So ENV dot P, yeah, PSAS. So this is the entire transition probability matrix for all possible actions. Okay. Similarly, if I want to see the reward function of this MDP, right? RSA. Yeah, this is the entire reward function for that environment. So you don't have to deal with putting up rewards, putting up transition matrices, anything. You just have to write this structure, and this grid world object will take care of computing PSA, RSA, everything. Okay, so just go
Sir, the
deal. Yeah,
Gridworld is free software, sir. You have to install it.
yeah,
Gridworld.
no. It is kind of a library that I developed
Okay.
during my BTech. So yeah, you can get it from, yeah. I can just paste it in chat. So it's very easy to like kind of get this the kind of interactive environments. Okay. And it's like how to install it, everything is there. It's in the README. You just go ahead, read the README. Only these 4 lines would install it, and then how to use it. There are kind of good explanations. So if you are going with an model free, so you don't have those models, right? PSA or RSA, right? Then in that case, you have to interact with the environment, take action, and then make your decisions kind of better, right? So in that case, also there is this interaction loop you can write. Where is it? Yeah, interaction loop you can write. Maybe we will discuss these things also. Okay. And
Okay,
if
so
you
it's
don't,
it's like
yeah,
it's like a library, so like
yeah,
NumPy or
yeah,
Matplot like that.
exactly.
Okay,
So it's a
okay,
library that enables you to build grid worlds from only
okay,
writing this pattern.
okay, sir.
Okay? And you don't have to think about how to define the transition matrix, how to define the reward model. It's already predefined.
Okay, sir.
Yeah, so it's basically like gives you a platform to test out algorithms quickly.
Okay, sir.
Okay.
Okay, thanks.
Okay. Okay, then let's meet in the next session. I guess next week. Okay, we may be covering more reinforcement learning algorithms, and also do the practice for week 9, week 10. Okay, week 9, week 10 questions will practice. Let's see. Yeah, but I guess the only remaining part in the syllabus is this expectation maximization. Oh no, sorry. This Gaussian mixture models, expectation maximization algorithm, and the HMMs, all those things, right? Yeah, those things I will cover one day. Okay, so the good part is this reinforcement part. So there can be lot of MCQs from here. Okay, okay, guys. Uh, let's meet next week. Yeah, try out the library if you want. Okay, and you can go ahead and watch the. So if you are not patient enough, let's say wait for next weeks for the algorithms to come, right? So you can just go ahead and watch the Stanford lecture. Copy paste. Yeah, this is from Professor Irma Brunskill. Okay, so which slides I used, right? You can also go ahead watch these lectures and get an idea of how to implement the algorithms. And those are all already implemented in the library. So if you want to go ahead and see how a particular algorithm is implemented, you can just go to sample examples, and all the kind of basic algorithms up to advanced like PPO, TRPO, all are implemented. Yes, you can go ahead and learn. Let's say I want to see policy iteration. This is an algorithm we'll see next week. You can just go ahead and see how it is implemented in code here. Okay, so this is the algorithm I was talking about, that you start with a random policy and then you improve until you are not able to improve any further. Okay, so you just improve. So the instead of this type of graph, you would have a monotonically increasing value graph. So this graph, you try out all the possibilities. So that's the kind of zigzag graph, right? If you just improve monotonically, then you will have a like upward value function growing graph. We'll see those things later on. Let's not, yeah, let's not go into that now. Okay, guys, so let me stop sharing. Also stop recording. Stop recording.